Okay, so the next thing that we're going to take a look at, we're going to do a quick review on solutions and also calculations involving solutions, which typically sort of center around the idea of molarity. So first of all, let's take a look at remind ourselves what a solution is. Okay, and a solution is a homogeneous mixture. Okay, so we're going to have multiple pure substances that share the same physical space but are not chemically combined with each other. So a solution is composed of two components. We have what's known as the solute, and we have the solvent, right? So the solute is the component present in smaller amount. Okay, and you can have multiple solutes. And the solvent then is present in greater amount. And there's only one solvent in a solution. So for example, if I have a container with some water in it and I added a pinch of salt and I stirred it up to dissolve the salt in the water, then I have a salt water solution. Okay, so in this case, the solvent would obviously be water, H2O. Okay, and then the solute here would be the salt. Okay, so that's a fairly simple example. Um, we talked about gases in one of the previous videos. So if I take a look at the air that, that's around us right now, the majority of the air that you're breathing in is nitrogen. And then you have a smaller amount of, let's say the blue ones here is oxygen. And you have even smaller amounts of other things like let's say carbon dioxide, for example, and other components of the air that you're breathing in. So again, you have a homogeneous mixture of several different gases. So air is actually a solution. You don't normally use the term solution, but it is. Air is an example. It's a homogeneous mixture. So in the case of air, okay, the solvent, I think present in greatest amount in the air is nitrogen gas. And then the solute, now we're going to have multiple solute. We have things like oxygen, we have carbon dioxide, we have other things like argon, etc. Small amounts of those things. The solvent N2 makes up about 78% of the air that you're breathing in, right? Oxygen is about 21%, and then the remaining here is about 1%. But obviously, the solvent present in greatest amount is the nitrogen. So my point there is solutions can actually be in multiple different physical states. It doesn't have to be a liquid like we normally think of for a solution. It can be in the gas phase as well. Okay, so what happens when solutions are formed, or when solutions form in the first place? So let's take a look at how that happens. Okay, so the key thing, uh, and again, we're going to use aqueous solutions as our examples in most of our examples. So aqueous solutions, we abbreviate as AQ. And again, the term aqueous means that water is the solvent. Okay, and remember now, water, based on what you know about covalent bonding, molecules, etc., is H2O. If we take a look at water, it looks like this. There's two hydrogens connected to the oxygen in the middle. It is bent, has a bent shape. The oxygen is more electronegative than both of the H's. Water is polar as a result of the differences in electronegativity and based on the shape of it as well. So the O here is going to be slightly negative. It has a slight negative charge. The H's are going to be slightly positive as a result. Okay, so you would have seen that before when you looked at covalent bonding in Gen Chem 1. And that's critical to how solutions form in the first place. So if I have some sodium chloride, regular old table salt, okay, a pinch of table salt, and I add that to some water. Okay, we know from experience that it looks like the salt disappears, but how does it actually do that? Well, what happens here is if I were to zoom in on a sample of this solution, what you would see is that the sodium chloride breaks apart into Na plus and Cl minus. And because you have a ton, not a literal ton, but a lot of H2O floating around, we can predict that that H2O molecule, and we have billions upon billions of them, will naturally orient themselves around each of these ions in a predictable fashion, and that fashion being the slightly negative O's are going to be oriented towards the slightly positive Na plus. No, not the slightly positive, but the positive Na plus, right? So opposites attract. So the opposite then would happen for the Cl minus, where the H's of the H2O, which are slightly positive, these will want to be close to the negative chloride ion. And that is what keeps the Na plus and the Cl minus separated from each other. So the waters, the H2Os, surround the Na plus and the Cl minus, and that process is called solvation. And specifically so solvation is surrounding the solute with solvent particles. Specifically, when that solvent is water, then it's called hydration because we're using water to solvate the ions. What this means then is that now you have ions in solution. So when NaCl dissolves, ions, we have Na plus and we have Cl minus. This leads to the solution being now an electrolyte, meaning that it can conduct an electric current, can conduct electricity. Okay, and in order for something to be an electrolyte is a substance, it's defined as being a substance that can conduct an electric current when dissolved in water. In order for it to do that, you have to have charged particles, right? And because this dissolved as ions, you're going to have a ton of these charged particles. So that's how your ionic compounds typically dissolve. They dissolve as ions. They get completely hydrated by the water molecules. It makes them electrolytic solutions. If you take a look at a different example, so if you have something like sugar in water, okay, so again, same thing. I have my water in here, my H2O. I take a pinch of sugar and I add it in. Okay, we know that the sugar dissolves. Right, it looks like it disappears, but how does it do that? Well, sugar doesn't dissolve as ions. Instead, table sugar, for example, sucrose has the chemical formula C12H22O11. This is a covalent compound, covalent molecule. And even in the smallest pinch of sugar that you have billions of these molecules. When you add it to water and you stir it up, what happens is it dissolves as individual molecules. So even though, right, you have whatever this is, 34, 45 atoms in this molecule, it is still incredibly tiny. It doesn't break apart into ions. So no ions. That are formed, it still does dissolve, so it does make a solution, but the water molecules come in and they surround each of the sugar molecules instead of individual ions. So because there aren't any ions in the solution, this would be a non-electrolyte. because there aren't any ions in this solution. But the solution still does form. It just forms by a different mechanism. Okay, so those are some it's a quick reminder of solution properties, and what they actually are. The next thing we'll take a look at is more on the math side of solutions. So when we try to quantify the components of a solution, so quantification of the components of a solution. And by the way, I will abbreviate solution as SOLN, just like reaction was RXN, equation was EQN, solution is SOLN. What we use, probably the most common way that we can describe the amount in a solution is a unit called the molarity. Okay, this is something that we see quite frequently. We learned about this back in Gen Chem 1. Molarity literally means moles of solute per liter of solution. Okay, so this is the most important thing that you want to remember when it comes to molarity. Moles of solute over liters of solution. So it relates one component of the solution to the entire solution itself, specifically amount in moles to the liters in the volume, I'm sorry, in liters. So for example, now we'll take a look at a couple calculation problems. So what is the molarity? Molarity, by the way, is abbreviated big M, uppercase M, of a solution made by dissolving, let's say, 15 grams of NaCl in a total of 125 mils of solution. Okay, so we want, just like with the previous examples, what are we given? What do we need to find? What are we going to use to get there? So we're given, in this case, mass of NaCl, right? Salt, that's going to be your solute. We're given the volume of the solution. Okay, what we need to find is the molarity. Okay, so what we're going to use, moles of solute over liters of solution. That literally is what molarity is. Well, are we given moles of the solute? No. We're given mass of the solute, 15 grams. Okay, so in order to calculate the molarity, we need to convert the 15 grams of NaCl into moles of NaCl. That's a gram to mole relationship. We're going to use the molar mass of NaCl to do this. Okay, and once you get that, you can plug it into your thing here. We're given the volume of the solution, 125 mils. Okay, the volume has to be in liters, so you want to convert that. 125 mils is the same as 0.125 liters of the solution. That's going to go in here, and we simply divide those two, and we end up with the molarity, right? So whatever we get, I'm not going to do the calculation. You can do that on your own as practice. The concentration of the NaCl will be whatever it is that we decided, right? So let's say X molar, right? M here being the unit. Sometimes you'll see square brackets around something. So square brackets around NaCl literally means concentration of that thing, right? That's a shortcut or an abbreviation. So when you see the square brackets, this means concentration of in units of molarity. All right. So that's how you calculate the concentration. You need moles of the solute divided by the liters of the solution. Now, if we wanted to make that solution, if you needed to make let's say 500 mils of a 1 molar NaCl solution, right? How would you actually make that? Well, first thing we need to do is, well, to make a solution, you need solute and you need a solvent, all right? So what's the solute? Well, the solute here is the NaCl. And we're told that we want to make a 1 molar. So 1 molar means 1 mole of NaCl in this case per liter of that solution, right? That is literally what it means. So if I had to make a liter of that solution, I would need a mole of the NaCl. Do I need to make a liter? No, I need to make 500 mils. So 500 mils is 0.500 liters. So if I take my concentration and I multiply it by the volume that I need to make, guess what? Liters go away. Now I end up with 0.500 moles of NaCl. That's the amount of NaCl I would need to make 500 mils of that solution. Well, can you go into the lab and measure out 0.50 moles? No, you don't have something that can tell you the number of moles. Instead, we want to convert that to mass in grams. So we need the molar mass for every 1 mole of NaCl, right? Sodium is 23, chlorine is 35, so that's 58.45 grams of NaCl. Okay, moles go away. So what's half of that? Well, that would be whatever, 29 maybe, 29.22 or so grams of NaCl. Okay, so I know how much sodium chloride I need to make that 500 mils of the solution. So what I would get is I would get a volumetric flask, so something that looks like this, a 500 mil volumetric flask, a flask that can measure only up to 500 milliliters. I'm going to weigh out my 29.22 grams of NaCl. I'm going to put, first of all, a little bit of water in here initially, maybe about 500 mils, maybe about 100 mils or so of water. I'm going to take um, my solutes. I'm going to add it in. Add solute to this. I'm going to stir it up to dissolve all of it. And then I'm going to fill to the line with the remaining solvent with the H2O, right? So when I fill this up here, give it have a stir bar or something in there or put a lid on it and shake it up. That's going to be my 500 mils of the 1 molar um, sodium chloride solution. So that's how you make a solution from scratch. Now, the other way that we can make solutions is by a process called dilution. Okay, and when it comes to dilution, what we're doing is we add solvent to a solution. When you dilute something, that is what you're doing. You're adding solvent to a solution. And when you do that, the following things happen. When you add solvent, obviously the volume will increase, right? The volume of the solution will increase. The number of moles of the solute is unchanged, right? So we don't change the amount of solute that we have, but because we're increasing the volume, what happens then to the concentration is the concentration would decrease. Okay, so that's literally what happens when you dilute something. You add more solvent to it, volume increases, concentration decreases. So we can mathematically express the dilution process by an equation, which goes like this: M1V1 equals M2V2. Or more generally, C1V1 equals C2V2. This should look familiar to you because it resembles one of the gas laws, specifically the gas law that where there was an inverse relationship. So what this means then, again, your ones here represent your initial conditions. The twos represent final conditions, right? So what this says then is as the volume goes up, guess what happens? The molarity goes down, right? That's the same inverse relationship we saw previously. And that's exactly what we would expect to happen based on just, thinking about what happens in a dilution process. So let's take a look at how we can use this. So let's say a 25 milliliters, 24.0 milliliters of a 0.75 molar NaCl solution is diluted to a final volume of 125 milliliters. What is the final concentration? So square brackets of NaCl. Okay, so just like with all the other problems, what are you given? What is it that you need to find, and what are we going to use to get there? So we're told that we're starting off with a volume. So my V1 here is 25.0 mils. I have an initial concentration, so my M1 is 0.75 molar. We're told that it's diluted to a final volume, so my V2 is 125 mils. And then we need to find the final concentration, so my M2 is my unknown. All right, so I'm given three things. I need to find the fourth thing. Obviously, these are all related by the dilution equation. Okay, my unknown here is M2. So if I rearrange my equation, I can divide both sides by V2. So this ends up being M2 being equal to M1 V1 over V2. I'm going to take these and I'm going to substitute them into my equation. So M2 is M1, so 0.75 molar. And I'm keeping track of my units because they will tell me whether I've actually done the algebra properly. So M1 V1 is 25.0 mils divided by V2, which is 125 milliliters. Milliliters go away. I have molarity as my only unit. That makes sense because I'm trying to find molarity. And the other thing to note here is once you get your final answer, let's say X, we know based on what dilution involves, we can predict that this final volume has to be, this final volume here must be less than M1, right? When you dilute something, the concentration decreases. So it has to be less than 0.75 molar. And if it isn't, that means you either use your calculator incorrectly or you did the algebra wrong. So you want to make sure that you use all those little tricks and tips along the way to help you um, not just get an answer, but process the answer. Does the answer make sense? Does it not make sense? And if it doesn't, well, then we can kind of troubleshoot along the way.